All right, we've been talking about energy starting Friday, and we'll talk some more about energy. First, a review of the things that we quickly looked at on Friday. We'll be looking at more of these things today. So first, our definition that work was the force multiplied by distance parallel. And I think it's the next slide after here where I have the equation written out again as a reminder that we can use a graphical analysis to find work. So I think I remember to put in a clicker. No, I didn't remember to put in a clicker question for, well, okay. Potential energy is defined only for conservative forces. Potential energy means you have the potential to do work because of the position or configuration of the system. And I just realized I didn't have the sound on for them over there. I asked them if they could hear me, and I didn't hear a response because I didn't have the sound on, but it's on now. So potential energy is defined as the negative of the work done by a conservative force. So for instance, gravity does a work of the force of gravity times the distance parallel. And so the potential energy for gravity is minus the work times the distance parallel. And finally, the equation we get for gravity is that. So potential energy for gravity is mg multiplied by the elevation. And one last thing that I don't have on this review here is the reference point for your elevation in potential energy for gravity can be wherever you want it. So you choose your reference point to make life the easiest for you. And, always putting a zero somewhere is going to make life easier. So as we start in again with energy, we're going to be doing some problems with energy. And of course, you've done some simpler ones. I say simpler because I know they weren't necessarily easy, but some simpler ones. It turns out that using energy, you can solve a lot of the same problems that in the past we solved with Newton's second law. And of course, some people might right off the bat say, why in the world do we spend all this time learning Newton's second law if we can solve them with energy, and many times it's going to be easier doing it with energy? And there are two really important reasons. Number one, and most important, in order to understand how the energy solution works, you have to first understand Newton's second law and how to apply it. So that was a building block necessary to understand how the energy works. And number two, sometimes it will be easier using Newton's second law. Now, why would one method be easier than the other? Hey, Joel. For most cases, energy is easier because energy is a scalar value. Energy doesn't have a direction. It's not a vector. And so being a scalar, having no direction, makes it easier to do your math problems. So that's the reason why energy is often the easier way to approach a problem. That's not the way that was supposed to look. Okay, there we go. There are three fundamental types of energy. You can make lots and lots of different types of energy. There's gravitational potential energy, there's spring potential or elastic potential energy, and so on. But every kind of energy can be broken down into one of three different types. Kinetic energy, energy something has because it's moving, which is the thing I'm really going to be introducing, the only new thing today besides power. Potential energy, energy it has because of its configuration. And rest energy. Rest energy was something that Albert Einstein introduced to the world. Albert Einstein proposed that mass is just a form of energy. Prior to 1905, people said that mass is conserved. That is, you have mass here, you do whatever you want with it, you still have the same amount of mass. So if I have, for instance, 10 protons and 10 neutrons, it doesn't matter what I do with them, it's going to have the same mass. But Einstein proposed that mass is just another form of energy. And so the equation associated with this is the rest energy. Put a little zero there to indicate the rest energy. And you've probably seen that equation, E equals mc squared. That's the rest energy, the amount of energy something has by virtue of its mass. And it's this equation here, that rest energy, that made it possible for humans to develop things like nuclear power and to understand how the sun is producing its energy. Because in something like a nuclear fission bomb, that is the kind of bombs that the USA dropped on Japan in the end of World War II, those bombs, the entire energy released is because you take uranium, I think it's 235, and split it into smaller atoms, and those smaller atoms have less total mass when you take the smaller atoms combined than the uranium had to begin with. And the difference in mass is released as energy. And so all that energy came from converting mass into energy that was, well, what do you call energy when something is moving? Kinetic. Now, some people would say, but it's not really kinetic energy, is it? I mean, what it makes is a really hot gas, and then that hot gas expands. Well, hot means that the molecules are moving really fast, right? Temperature is a measurement proportional to the average kinetic energy of the molecules. So if it's hotter, that means the kinetic energy of the molecules is faster. Because we can't sit there and look at each molecule, we talk about the temperature, and that is a macroscopic measurement of the microscopic kinetic energies of the particles. Okay, so just a little about the types of energy. So our first clicker question, one that we had last class period, there's. Okay, so it is accepting answer starting now. Aaron, you were the first one in. So we already have this. What kind of forces have an associated potential energy? As we see these words, liberal, conservative, I am reminded that tonight there is a presidential debate for anyone who has the stomach for the two major candidates. We are forbidden to stand up here and espouse anyone, but I will say that I cannot, in good conscience, espouse either of those two people. If you plan on doing something else, you can, Maranatha, tell them what they could do.
You can get free Chipotle if you join our free health professional club.
All right, so there's a better well, not a better thing, but something that will cost you less headaches to go to Chipotle with the pre-professional club. All right, so ending our polling here, we had a strong majority who remembered from last time that it's only conservative forces. Now, since I broached the debate in politics here, let's talk about what conservative means. What does conservative mean in politics? Because it's similar. No one?
Attempt at it, like an error on the side of caution when making decisions.
Okay, I have a student, Colton, that said to err on the side of caution with making decisions. That's not bad. That's a pretty good definition. The traditional definition of conservative is wanting to keep things the way they are, not wanting to change. Whereas progressive is changing. You may be moving forward, you may be moving backward, but you're progressing, you're changing away from the way things are. So that's the difference in a progressive and a conservative, although I am sure all conservatives believe, or all progressives believe they're moving in a better direction. I'm sure there's no conservatives or progressives that believe, yes, we're taking this place to heck in the handbasket. Here we go. Right? That's not the way they do it. I hope. In physics, conservative means the same thing. It means not changing. If you're conservative politically, you want to keep things the way they are. Conservative in physics, you want to keep things the way they are. And Emmy Nether did a mathematical proof, right? We can't prove things with experiment, but with math we can. She did a mathematical proof that shows that according to our understanding of the laws of physics, the energy must ultimately be conserved. That is, you can't gain or lose energy. It can only move from one place to another. Now, with that in mind, Emmy Noether says we can't create or destroy energy. Why do we worry about green energy? Jordan.
The energy is going into thermal energy, and which has negative impacts on the environment.
Okay. Jordan focused on the output part, that when you use energy, you convert it from some type that's usable into a heat energy that's not very usable to us. And that's a real, it's the reason we have to have an issue with this. But the other side is what I was looking for. We don't create energy when we pump oil out of the ground, or we don't create energy when we grow a tree to burn, right? That energy was converted from something else. But we are using energy, converting it from one source that is readily usable into one that's generally not, as Jordan said. And so oil, by the general definitions, is a non-renewable resource. Oil is renewable over, time span of thousands to billions of years, depending on who you talk to, but it's not renewable over the course of a year or two or even a lifetime. So that's why we consider oil a non-renewable resource. We use it up, it's gone. The U.S. has a long-standing policy, which has broken down in the last decade or so, of trying not to use our oil reserves and use other countries' oil reserves, and then when they're out, then we'll be king of the hill because we'll have the energy. Obviously, recently the U.S. has been using a lot of our oil, which has caused gas prices to come nicely down, which we all appreciate. People in Oklahoma who are having earthquakes that are believed to be caused by the fracking don't appreciate it as much as those of us who are out here in a craton that doesn't move at all. So energy conservation, green energy, those are because we can't rely on things that we use up. So we have things that are always renewable. Over 99% of the Earth's energy budget, all the energy the Earth uses, comes from the sun. And unlike some senators have opined in Congress or Senate, I guess senators are in Senate, we can't use up the sun, right? People have actually said, being serious, that if we have solar panels, well, we'll use up energy from the sun and cause the sun to burn out quicker or something like that. Not the way it works. But solar energy is a great source of energy because it's plentiful, right? Especially if you're like in the Southwest, Southwestern students, you've got sun all over the place. You can collect that energy and it's, pretty much free. What's the downside? It's expensive to make those solar panels. There's a lot of pollution involved. So there's upsides and downsides. It's a great debate, but it's something, especially I think as Seventh-day Adventist Christians, we should be caring for God's world and looking into those issues and trying to not destroy nature. Okay, that is actually part of this chapter, in case you're wondering about that little deviation from anything on these. I didn't have it in my slides, but had to cover those sources of power. Okay, so one thing to say about what we're doing in this chapter, we're only talking about translational kinetic energy. Translational means traveling in a straight line. There's also kinetic energy associated with rotation, and we'll learn that later. Also, we're not talking about internal energy, that is the energy from vibration of molecules or molecules flying around the room. We're only talking about kinetic energy of things like balls flying toward you. There's the equation again for work. Just to remind us, work is force times the distance parallel to that force. So dot product means we're only multiplying the parallel parts. This is a way of writing the dot product without using vector signs and the dot. Or the magnitude of the dot product, since dot products are only magnitudes, is just force delta x times cosine of the angle between, as we talked about on Friday. I think I'm done reviewing. Any questions before I move to new material? Or what I think is going to be new material? I see no questions. Okay, here's a statement that I haven't made in the past. And it's a statement that sometimes bugs me, so I added the bold part to make sure that we're clear on this. You'll read in your textbook, normal force does no work. And with a mass sitting on the desk, yes, the normal force does no work. But if I have this here, the only force acting on this is gravity, and normal force went sitting in there, and I raise it up. Okay, I did work on this box, but then the normal force of this box did work on this mass. And so oftentimes people forget that aspect. If the surface is moving, then the normal force can do work. So normal force does no work when it is perpendicular to the displacement, when something is, when it's not lifting. An elevator floor, that normal force will do work on you to lift you up, right? So if a person's sliding down the slide, that surface is stationary, it's not moving, the normal force in that case does no work. Colton has a question.
I've actually had questions before and never asked it, but why is the normal force associated with the perpendicular point to the surface if gravity's always going to be, I guess perpendicular to the Earth's surface?
There's a flippant answer, which is not going to help you, and that is because normal force is defined as in the normal direction. The more realistic answer is normal force is not defined with regard to gravity. If I come over here and I push on the wall, there's no gravity involved with me pushing on the wall or with the wall pushing back to keep my hand from going through. The normal force is the force coming out of the wall to keep my hand from going through. So it's not specifically tied in with gravity.
Okay.
We oftentimes think about that because, when something's sitting on the table, normal force is opposing gravity. Good question. Okay, now the first of our problems. I put the equations down below. I was like, I used to have the equations on here. We're going to talk about kinetic energy and how it relates to this roller coaster. So we haven't discussed kinetic energy yet, I don't think. We didn't talk about it Friday, did we? I don't think we did. That's why I took the 3 questions out of the homework and replaced them. So kinetic energy, the energy in motion. I have a slide that I took out that shows how you can use calculus to integrate and find the kinetic energy. We're not going to do that. We're just going to go straight to the answer. Kinetic energy has an equation of 1/2 mass times speed squared. So that's saying something can do work because it has mass and it's coming toward you. Now, let's take a simple example. I hope I haven't used this in this class yet. Let's say that Gila and I are running down and we're going to tackle somebody. And for some reason, Gila and I have exactly the same maximum speed. So we're going to have the same speed. But of course, I have a mass that's about 3 times the mass of Gila. So putting this in very layman's terms, which one of us is going to do the most work on you when we tackle you? Gila or me?
Yeah.
Me. We all understand this. We all know I don't want to get hit by Richard going full speed, because Richard going full speed is going to have a lot of kinetic energy. Now, you don't necessarily know it's a lot of kinetic energy, but it's going to be able to do a lot of damage, right? Richard doesn't have to have any strength as long as he's moving because it's 1/2 mv squared. Gila with the smaller mass, she would have to go a lot faster to get the same kinetic energy. So that's what the kinetic energy is, its ability to do work. If I run into you, I'm going to make you move. How much I make you move is going to depend on how much kinetic energy I have. And of course, you can brace yourself and those kinds of things. But assuming that you are like standing flat-footed, it's your mass, my mass, and a few other things, my speed. So kinetic energy is the ability to do that work because you're moving. And we have this equation right above that is a very important equation that is the relationship between work and energy. That says the net work, that is add up all the different works, and that's equal to the change in kinetic energy. Now, take one of your homework problems. You have a problem where there's a person being lowered down a slope in a, I assume a Stokes basket or something like that, and you have the forces and whatnot. The problem is, careful to say constant speed. The reason it says constant speed is that means that the kinetic energy is staying the same, hence the change in kinetic energy is zero. And if the change in kinetic energy is zero, what does your total work have to be? Good answer, Gabriel. Did that before breakfast. I was late to breakfast. Got the scolding. So because we had not studied kinetic energy yet, it didn't mention kinetic energy in any way, but it had that statement there to keep things so there's no discrepancies in the problem. So work net, add up all the works, change kinetic energy. Now we have learned about potential energy, and we learned that potential energy is equal to minus work conservative if we have a conservative force, such as gravity. So in this problem here, we are assuming no friction. Does it say that somewhere? Yeah, I don't think it says that. But we're assuming no friction. And the force normal is not going to do any work. So if there's no force friction, there's no force normal, force normal does no work, then the only work that's going to be done is going to be the work done by gravitational force. And so we're going to have my work net is equal to the work done by my conservative gravitational force, which is equal to minus the change in, I forgot a change in sign. You do have to correct me when I forget things like that, because that's really important. Potential energy is not equal to work. It's change in potential energy is equal to work. So the work net here is minus the change in potential energy. And so I can take, work net equals minus change in potential energy equals change in kinetic energy. We usually rearrange this to say that 0 is equal to change in kinetic energy plus change in potential energy. That's true because there is no friction. What if there was friction involved?
It's not a conservative force.
It's not conservative. So my work net, if there was friction, work net would be equal to work conservative, that's not a W, plus the work non-conservative. The work conservative is still minus change in potential energy. So this would be, put the work non-conservative here, minus change in potential energy, and I would have had my equation. So this equation here is generally true. The work non-conservative, that's the work done by friction, or if you're sitting there pulling a rope, you're not conservative. You think about this, you're lifting weights. Guys, laying on the bench, you push that bar up, you did work on the bar because you had that force. Let's say you're at the NFL Combine, 225 pounds. You moved it up a meter. You did a work of 225 pounds times 1 meter. Well, we're in mixed units, but you did a certain work on it. When it comes back down, do you get that energy back? No, you don't. So you're not conservative, right? You can't sit there and pump all day because you're not conservative. So you would be a work not conservative. But this equation here, that's the common work energy relation we use in physics problems. That's what we're going to use for the next problem after this as well. So now we want to look at this and say, start at the top with 0 speed. How fast is it down here? If you were to do this with Newton's second law, it would actually be really hard because the angle of the net force is constantly changing. So you'd have to calculate what your acceleration is at each different location, do some calculus on it. No one wants to do that. Now, of course, you do have dot products involved with that calculus that makes it so you can do it. But if you do it with work energy, you don't have to worry about those directions. So doing it with the work energy approach, all I do is I say, well, my network is changing kinetic energy plus changing potential energy. So I'm going to find the kinetic energy and find the potential energy at each point I'm interested in, and then put it into that equation. So if we come and look at the positions here, initially, what's my kinetic energy initial here? 0. Why is it 0? Because velocity is 0. So it starts with 0 kinetic energy. How about its potential energy here? You have to answer a question before you can really give an answer to that. You have to decide where are you going to use your reference point. And to make my life easy, because I have two heights that are defined with respect to the starting point, I'm going to consider the starting point 0. So I'll be able to use 0 for both of them. So I'm just going to say this here is y initial equals 0, so my potential energy was 0. So this here is going to be y1 is equal to minus 25 meters. Why minus? Because it's below. And so now I need to know what my kinetic energy and potential energies are at the bottom. So in terms of equations, what's my kinetic energy 1 going to be? Right, 1/2 m v1 squared. And my potential energy 1? Go ahead, answer. Okay, it's going to be mg, and I'm going to put y1. H was the elevation, so I'm using y here for the elevation. So I put y1 for the h there. So there's my kinetic energy 1, my potential energy 1. I can go over here and do the same things. Here I have y2 is equal to minus 20 meters, and I'll have the same equations except for 2's. So now using this equation, work non-conservative was 0 equals kinetic energy 1 minus kinetic energy initial plus potential energy 1 minus potential energy initial. Right, I did change in, so that's always finest minus initial. Substitute our values, 1/2 m v1 squared minus 0 plus mg y1 minus 0. And then we're trying to find the speed, so to solve that for speed, one of the things that's real important to note here is what happens to the mass. I have it on two masses here, and it's equal to 0. So I'm going to have 1/2 mass v1 squared equals minus mass g y1. And I can cancel the masses from both sides, multiply both sides by 2, and I have v1 squared is equal to minus 2gy1. You might think I have a problem here. One thing you note is it doesn't matter how much mass the roller coaster cart has, it's going to have the same speed if there's no friction or air resistance. Why does this look like I have a problem? Because I have a square root of a negative. But if I put in my numbers, minus 2, g is always a positive value. So g is a positive. That doesn't get rid of anything. But then I have my y1, which was minus 25 meters. And so I have the square root of minus 2 times 9.80 times minus 25. Minus times a minus is a positive. 50 times 9.8 is going to be 490. Square root of 490. I don't know because it's got the extra 0. Right, if it was 49, we would have known the answer. So somebody just calculate real quick. 22.14. Oh, and I got to put the square root sign on both sides. So I'm going to have 22 point what? 14. Now here's a quick question for you. When it gets to the bottom here, it's horizontal. So it's traveling horizontally. How would the speed differ if it was traveling vertically at the bottom? Like if the track went whee, and so you're going vertically down when you get to that point. How'd the speed differ? It'd be the same because direction wasn't part of this. All that mattered was the change in elevation. And now, of course, after doing the first one, we could easily find the finish speed by doing the same calculation, but replacing the minus 25 with the minus 20. So that is a simple type of work energy problem. In a moment, we'll do a slightly more complicated work energy problem, another roller coaster problem, because I like roller coasters. But first, we're going to consider another situation for conservation of energy. So if I have a pendulum, and here I have the makings for a pendulum, I have a cable that I'm going to hang from the ceiling. Not fall on my desk. And from this cable, I shall hang my bowling ball. Maybe. There we go. Okay. So I have the bowling ball. They can swing back and forth. It's a pendulum. Now with this pendulum, what do we know about the force of tension here with respect to the motion? The direction is what? Okay, the direction is perpendicular. So if the force of tension is perpendicular to the motion, what does that tell you about the work done by the force of tension? 0. Even when it comes up like this, if it's swinging, the tension will still be perpendicular to the force, or the force tension will be perpendicular to motion. No work done. So if there's no work done by that, and if we could ignore air resistance, then there'd be no non-conservative work of any type. If there's no non-conservative work, what does that tell you about your change in kinetic energy and change in potential energy? They add up to 0. We actually define the total energy as the sum of kinetic energy plus potential energy. We call that the mechanical energy, and for now we call it total energy. So the total energy would stay the same, but energy is going to shift back and forth between potential and kinetic. Now, what aspect tells me how big the potential energy is? My hand is telling me the answer, of course. What tells you how big the kinetic energy or potential energy is? The elevation, of course, plus the mass of G. The elevation. What about the kinetic energy? The speed. So if it goes higher, what happens to the potential energy? It goes up. So if the potential energy goes up, what has to happen to kinetic energy? It has to go down. So now we do our classic demonstration. Now this classic demonstration is I take this up, I stand, and the tricky part is to stand so I won't lean forward or backward after I release. I stand, I hold up to my chin, I let go. Swings down, comes back. What's going to happen to me? In theory, I should be good if I stay still. The scary thing about this is you have to stay still. When I was teaching at PHYS, I had a wall I could stand against. That was good. I just put my head against the wall, it's not going to move. So, it worked, right? Did I flinch? A little bit. It's hard. I trust physics completely. Myself, not nearly as much. Another interesting thing about physics, you notice that thing up there is not perfectly stable. It twists around. So if I let this thing swing, it will start to go sideways and eventually hit a desk. So I can only let it swing a little bit. If I just walk away, yeah, we'll eventually have a bang. And, well, this used to have a smaller hook on before I broke it last year. So we shall stop that. And because this kind of gets in the way of their video, I have to take it down again before I go on. So this demonstration is an example of that conservation of energy, of the fact that the energy was switching back and forth between kinetic and potential energy, but not being created, so it didn't come up higher, not being destroyed. But then again, you may have noticed it didn't quite get to my chin. Why not? Okay, I may have flinched, but if I was perfectly a statue, it still would have gotten to my chin. Because air resistance. Sorry, I didn't give them time to answer. Air resistance is going to take away a little of its mechanical energy. It doesn't take away energy, it takes away mechanical energy and puts it into motion of the air molecules, which is heating up the air. So that's where the energy went away to make it so it didn't come up quite as high. Now, while I'm playing with things, I have this. Now, you can do this with just, a basketball, a tennis ball. It does the same thing. If I take my little super ball and I drop it, it bounces up. It has a coefficient of restitution of somewhere around 60%. It gives back about 60% of the energy when it bounces. Not great, but good enough. This here has 3 balls on it, so, it bounces as well, but you see the ball's kind of, bounced around. Put this on, this here can slide on and off, and then I try to drop it straight down. What do you suppose is going to happen? Has anyone ever seen this before? Okay, yeah. A few people have. Have you not seen Jonathan?
I've seen it.
I've seen it, okay. Anyone who hasn't seen it, want to guess what's going to happen? Megan.
The red ball's going to bounce off the yellow ball and come back higher.
Okay, Megan says the red ball is going to bounce higher. Okay, we're scientists I'm a scientist at heart. I want to see these things. I love to do this. I used to get out of the gym and do this. So I take it now. The real trick is I have to drop it vertically, which is hard for me to do. See, I shot Isaac in the leg. He's now maimed for life. Thank you, Colby. So we try again. Or maybe I should have another scoop so I'm not embarrassed. Okay, so we saw it shoot up and hit the corner of the room. One would immediately say the kinetic energy this ball had going down was smaller than the kinetic energy it had when it came back up. Because it shot up very quickly, went to a higher elevation, which you can only do if it has more kinetic energy. How does that happen?
Is this consistent with mechanics of springs, or is it just similar?
There are similar aspects to it. This is dynamic, and we usually think of springs more of a static thing. But we shoot things with springs, but we don't think about this happening when we bounce stuff off the spring. Jordan. Oh, wait, let Mahala doesn't answer the question, Jordan.
I was going to say it gains the energy that the other 3 balls have on it.
That's exactly right. When it hit the ground, if we were able to watch this in super slow motion, we would see that when the blue ball hits the ground, whoops, there. At least it's not bothering me anymore. It's on the floor understanding. Okay, when the blue ball hits the ground, it's going to be initially compressed right there. And it actually sends a shock wave that goes through the blue ball. So if you can watch it slow motion, you can actually see that wave traveling up through it. And when that wave hits this one, you have energy from this one gets transferred into the next one. And then shock wave goes from there to the next one, goes to the next one. And along the way, it's transferring energy that was in the blue ball, the rebound of the blue ball, into rebound of the green ball, into rebound of, I don't know what's called that color ball. And then eventually gets transferred into the red ball, which has nothing to stop it, goes shooting off. So you're exactly right, Mahalo. So it's not defying anything in physics. Likewise this. Now this is much more what you think about with the spring. This is half a ball. I can take the ball, I can bounce it. Bounces a little bit, not very good. I flip it inside out. What am I doing to it in terms of work and energy when I flip it inside out?
Applying tension.
Well, I put a force on it, which did work on it. And so this, because it's rubbery stuff, not plastic stuff, it's storing that energy. So now I put it on the tabletop, and at some point, it will rebound and return that energy, and that's exactly like a spring does. So the work I did to deform it is going to come back, and we'll see it pop up eventually. So Moving on. Now pay attention, Gila. How to solve work energy problems. We just did one. Now let's just make sure that we formalize exactly how we want to do this. So the first thing you want to do is to draw your diagram of the situation, just like everything else. When you're doing a force problem, you're going to need to put a free body diagram. If it's a work energy, you may not need a free body diagram, but you probably will need to have some aspects of forces there because work is done by forces. Calculate the kinetic and potential energies at the start and end of the problem. Right? So if there's friction, of course, then we have to go through the problem to calculate how much work was done by friction. That's in step 3. Determine if there are any non-conservative forces, and if so, calculate the work done by the non-conservative forces. But the potential energies, kinetic energies, just the before and after. And then use this form of the work energy relation that says the work non-conservative is equal to the change in kinetic plus change in potential energy, and solve the problem. It's a very straightforward method. There you see it shot up and hit the roof. Boy, I did a lot of work on that, right? So that's how we're going to solve work energy problems. That's what you're going to be doing for homework for the next couple days. So here is a problem. Now, we already looked at the first part of this. You might remember that I got all excited, drew my free body diagram, and then realized they didn't ask for the force normal. They only asked for the speed. The numbers here are different because I recopied the problem so it'd be clear. But let's just go through all 3 parts of the problem now. So the roller coaster has a vertical loop. It has a smaller radius at the top so that it doesn't have to go as fast. What does the radius have to do with how fast it has to go for you to stay in the seat? Why are those even related?
It's going to decelerate once it hits the upward slope.
It's actually not about that. It's not about decelerating as it goes up. What did you say, Aaron?
Because the radius of curvature is related to the centripetal acceleration.
Yes. The centripetal acceleration is v squared over r. So if you have a smaller radius for the same speed, you'll have a bigger acceleration. Why is that important? Because you're going to stay in that seat as long as the centripetal acceleration is greater than 1g. Why greater than 1g? Because gravity gives you that 1g. And so if the centripetal acceleration was exactly 1g, you'd essentially be floating at the top. If the centripetal acceleration as the acceleration you need toward the center is bigger than 1g, then there's going to have to be an additional force besides gravity pushing you down. And so that's going to be the force normal, so you're going to be being pushed down by your seat if the acceleration is bigger than 1g. Did you have a question, Isaac? No. Okay. So in this problem, for part A, it says, what's the speed of the roller coaster at the top if the radius of curvature is 15 meters and the acceleration is 1.1 g's down? So I'm just going to say, AC is equal to v squared over r equals 1.1 g. That means and it said 15, yep. So v squared is 15 times 1.1 times 9.8. If I square root that, v is equal to, and of course, if you do the square root, technically you have a plus or minus. What do I get for 9.8 times 15 times 1.1 square rooted? Okay, now we only have 2 significant digits, but make sure you keep all of the significant or all of the digits for continuing your problem. In that homework problem that I worked this morning for Gabriel, he had a question because at the end, if you add up the numbers using correct significant digits, you get a number that's quite a bit different from 0 because of dropping off digits. But if you keep your full digits, you find the right answer. So I think, it was 0 with an uncertainty of something like 1,000, So here we have plus or minus 12.72 meters per second. What difference is a plus or minus? Well, depends on if you're going left or right. For our problem, we don't care. So I'm not going to worry about the plus or minus because that's just telling us which direction it's going. So there's the speed it has to have at the top to have the 1.1 Gs at the top. Then the second question says, how high above the top of the loop does the roller coaster have to start to have that speed? So I'm going to draw an additional picture here. So I'm going to call this h equals 0, or y equals 0, excuse me. Y equals 0 when you're at the top of the loop, so that I can calculate y initial is equal to h, where h is this height above. So I have my roller coaster car that starts here, goes down the track, comes up, and I'm looking at it right here. This is a problem that lends itself perfectly to work energy. If there's no friction, then it's going to be reasonably easy. I don't have to know how long the track was or anything like that. All I have to know is the difference in elevation. So looking back at the steps, which you may or may not have written down, I'm sure everybody knows you can just read the slides after class, or actually before class, by looking at the link there in the Moodle website. What information do I need to have to solve this problem? Yeah, I need the kinetic energy initial and the potential energy initial, the kinetic energy final, and the potential energy final. So how high does it have to start from rest? If it starts from rest, what's my kinetic energy initial?
0.
Bingo. I defined my 0 position as the top of the loop, and the starting is h above that. So what's my initial potential energy? mgh. My final kinetic energy? 1/2 mv squared, where it's this v right here. And my final potential energy? 0. Now the next step, so that was step 2 there. Step 3 is, do I have any non-conservative forces? And in this case, I'm assuming negligible friction and air resistance. So my work non-conservative then is 0. And that's change in kinetic energy plus change in potential energy. So I have 0 equals kinetic energy final, 1/2 mv squared, minus kinetic energy initial, plus potential energy final, minus potential energy initial. And I can immediately solve that for h. Notice once again the mass cancels. It didn't matter. So h is v squared over 2g. Now, I'm going to go a step further on this. I'm not going to put in the number for v. I'm going to come back and look at my equation for v squared. V squared was 1.1 gr. My g's cancel, and my answer is just 1.1 over 2 times the radius. That's a pretty easy calculation. You can see it's easier to go back to my equation than it was to actually use the number. So you know that's going to be ever so slightly bigger than half of 15. So let's say 8-ish among friends. What was that? 8.25. So now I know it has to start 8.25 meters above the top of the loop to have the speed necessary to give it 1.1 Gs. And then the final part of the question says, it actually starts 5.5 meters higher. Oh, then my answer. If it's 5.5 meters higher, what happens? Right? If instead of 8.25, it's only 5.5? Yeah, it doesn't make it up. It'll come up somewhere like this and then go back down. And that's not as fun. But it says it's 5.5 meters higher than that. and that it loses the energy so that it has that speed. Now it asks me to find what the work non-conservative is. Work non-conservative is change in kinetic energy plus change in potential energy. So using this new information, that's still going to be the change in kinetic energy is going to be the same thing as we had before. The change in potential energy is going to be bigger by 5.5 meters. And so I'm going to have why did I write it like this? Because I know that if I take this here and this part multiplied by that those give me 0. Right? That's what I just calculated. And so I have the extra 5.5 meters, and so I can immediately say the work non-conservative is equal to minus mg times 5.5 meters. You see they gave us the mass for this last part because you have to have the mass to actually get your number here. I see people getting their books together, and I'm already over time, so I guess I have to stop. Sorry.